Hello lovelies. In this video we're going to be going through some exam style questions looking at Hess's law and bond enthalpy. Now there are lots of skills in this, and if you're not sure about any of the mole calculations or anything like that, then you can go and watch some other videos in this playlist where we take you through the basic skills. But this is looking at some quite complicated exam questions, and we're going to walk you through exactly what the examiner would be looking for.
Hi there, so here we're going to have a look at some questions on Hess's law and bond enthalpy. So this is perfect practice to make sure that you've got a good understanding on this topic. And I know a lot of people find this topic really quite challenging. So this is a perfect opportunity to get rid of all of those misunderstandings and to master it. Okay, so let's have a look at question 1 here. We're told that Hess's law is used to calculate the enthalpy change in reaction for which it's difficult to determine a value experimentally. And we're just asked here just to state Hess's law. So Hess's law is the fact that the enthalpy change of a reaction is actually independent of the path that is taken. So long as you end up with the same final state and you had the same initial state, the reaction is going to have the exact same enthalpy change. And this principle we're going to make a lot of use on in lots of questions in A-level chemistry. So this next question is all about bond enthalpy. So we're told that enthalpy changes of reaction can be determined by using mean bond enthalpies. Here we're asked to state the meaning of the term mean bond enthalpy. So this here is another definition I would recommend that you learn. So if you don't know this, when I write it down, then get a flashcard out and copy it out and then get quizzing yourself on it. Okay, so the mean bond enthalpy is the average amount of enthalpy or energy required to break 1 mole of covalent bonds in their gaseous state. Now, of that, there's a couple of really important elements to that definition. So it's very important that you know that we're talking about breaking 1 mole in particular of covalent bonds. And it's also very important that you know that these have to be in their gaseous state. So we can't have like liquids or solids or anything. We have to be looking at bonds that are currently in their gaseous state. So those are our key phrases, key words in that definition that we do not want to miss out. So next up, we're asked to suggest why the mean bond enthalpy of a C-double-C bond is less than twice the mean bond enthalpy of a C-C bond. So the reason for this is that in that C-double-C bond, that has a pi bond, and the pi bond is actually weaker than the sigma bond that we find in C-single-C bonds. And so that there is the reason why that bond enthalpy is less. So next up now, we're asked to actually calculate the value for the standard enthalpy change of combustion of propene in this particular reaction. So we need to know that to work out bond enthalpy using this method, we need to work out the sum of all the bonds broken and all the bonds made. And our enthalpy change is going to be equal to the sum of the bonds broken minus the sum of the bonds made. So to do this, we're going to have a think about all of the bonds that get broken and all of the bonds that get made. So in terms of the bonds getting broken, you can see here that we have propene and 4.5 oxygen molecules. So if we look at the bonds being broken, if we draw out the propene, that will help us. So you can see we have 3 carbons here and 6 hydrogens, and then we have 4.5 of those oxygens. So when it comes now to working out the bonds that we're breaking, we can look at our little diagram and the table to work this out. So we know that the enthalpy change is the sum of all of those bonds broken. Let's go through them one by one. So here I can see that I have one C single C bond. So one of these guys. So I have 347. Then looking at other bonds, I can see I also have a C double C bond, which has an enthalpy of 612. So I can see I've also got quite a lot of carbon to hydrogen bonds. So here in total, we have 1, 2, 3, 4, 5, 6. So I'm going to do plus 6 times this carbon hydrogen enthalpy, which is 413. And finally, I can see that I also have 4.5 of these oxygen bonds. So that means I'm going to add 4.5 times by 498. So now we've done that, and that's great. Now we need to work out the bonds that are made. So looking at what we have, I can see I've got carbon dioxide, which is carbon with a couple of oxygens. And I know that I have in total 3 of those. And I also know that I've got 3 in total H2Os. So looking at the bonds that I have here now, I can see that I've got, for every 1 carbon dioxide, I've got 2 C to O bonds. But I've got 3 carbon dioxide, so I actually have 6 of those. So I've got 6 of those carbon to oxygen bonds. And then very similar with the water, I can see for every 1 water molecule, I have 2 O to H bonds. But I've got 3 waters, so I actually have 6 of those as well. So now we have got everything there that we need. We can type this now into the calculator and get our final answer. So now by putting it into the calculator, I find that delta H is equal to the total of the bonds broken, which is 5,678, minus that total of the bonds made, which is 7,614, and altogether that gives us our standard enthalpy change of combustion of propene to be minus 1,936 kilojoules per mole. So that there is our final answer. So now we have a very similar question, but it's got a twist. And I find it increasingly nowadays in A-level chemistry, you're going to see them look much more like this than like the previous one. Okay, so here they've actually given you the answer for the enthalpy change. They've told you that the enthalpy change of this reaction is 210 kilojoules per mole, but they're asking for the bond enthalpy of a specific little bond within what we have here, for the carbon monoxide bond. So in order to do this, we still need to use the exact same equation. The enthalpy change is equal to the sum of the bonds broken minus the sum of the bonds made. That is still the exact same equation that we're going to use. So we have a problem here, I suppose, in that we don't know the bond enthalpy of the carbon monoxide, but that's fine, that's what we need to find. So if we were to look at the individual elements, so say if we look at the bonds that we are breaking, we have methane, and we have water, and we just have 1 of each. And you can see here that we have 4 of these C to H bonds within the methane. And for the water, we have 2 of these OH bonds. So we can go to our equation here, and we can see that the sum of our bonds broken is going to be equal to 4 times 413 plus 2 times 464. Now, we also know the enthalpy change, so we can fill that in our formula as well. We know that that's equal to 210. So now when we look at the bonds being made here though, we have carbon monoxide, which we don't know anything about currently, and then we've got 3 times H2. So that means that we have 3 of these. So looking at our formula, we know that the enthalpy change, 210, is equal to the bonds broken minus the bonds made, the sum of the bonds made. So we're just going to write carbon monoxide, because we don't know what that is currently, plus 3 times 436. And now we'll have a good chunk of the marks here already, because we have laid out our equation, we're looking good. Now what I would recommend that we do is we don't rush this, okay? Let's simplify each of these brackets, and then after that we can start simplifying and rearranging a bit more. So if we do 4 times 413 plus 2 times 464, we get 2,580. Now if we also work out what 3 times 436 is, we get 1,308. So now we've got a much simplified equation. Now we have one annoying little factor here of this negative sign, and negative signs I always think can cause a lot of issues. So let's multiply out this bracket, not forgetting the negative, okay, because that will be where we make mistakes. So we have a minus CO minus 1,308. So now we can simplify a little bit more. Let's work out what 2,580 minus 1,308 is going to give us. So I now make that 210 equals 1,272 minus carbon monoxide. So now let's subtract 1,272 from each side. So I now make that minus 1,062 equals minus CO. Now they're both negative, so we can say that the bond enthalpy for the carbon monoxide bond is equal to 1,062 kilojoules per mole. And that is our answer. So here we have another enthalpy question, but again, it's using a slightly different method. Now looking at this, we're told that a student carries out an experiment to determine the enthalpy change of a reaction directly. So we're looking at the reaction where A plus B becomes C plus D. So we're told here that the student adds an excess amount of A into 50 centimetres cubed of 0.1 mole per decimetre cubed of B. The initial temperature of the solution was 25 degrees C and the maximum temperature was 65 degrees C. And we're asked here to calculate the enthalpy change of this reaction. So there are 3 methods really that we learn in the first year of A-level maths to calculate enthalpy changes. The first one would be using Hess's law, the second one would be using the bond enthalpies, and the third one is using the equation Q equals mc delta T. Or you may have learnt that as Q equals mc delta theta. Both means the same thing. So we can tell when this is the question we need to use, when in the text of the question they tell us what the specific heat capacity is, because specific heat capacity is the C in this equation. And there's no other equation that we learn about at this level in chemistry that uses this constant C. So we know that this is what we need. So to work out the enthalpy change, we use this, but there's some common mistakes that will happen here. What this equation is going to give you isn't actually the enthalpy change, it is the energy in joules. Now what we need though in this question is the enthalpy change in kilojoules per mole. So if in a question like this, we consider finding Q to be our step 1. Our step 2 would be to convert Q from joules into kilojoules. And we will do that by dividing through by 1000. Then our third step in a question like this is to take your Q, which is now in kilojoules, and divide it by the number of moles. So maybe we'll need to calculate the moles in the question, but that's how we calculate delta H, by taking the Q in kilojoules and dividing it by moles. And then we do have a final check that I would recommend we do, is just check, is it exo or endo? So we need to look at the temperature change. And if the temperature change of those surroundings that we're measuring has increased, then that will mean that our delta H is actually a negative value because it is exothermic. Whereas if the temperature has actually gone down, then our delta H is going to be endothermic. It will be positive. Okay, so these are the things to keep an eye out for in these questions. Okay, so let's put this all into practice with this particular question. So here we're asked to calculate the enthalpy change of this reaction. So you can see here that we are given a certain amount of things. So we are told the temperature at the beginning and the temperature at the end. So we can use these two values to work out what the change in temperature is. The change in temperature will be 65 minus 25, which is 40. So we know that delta T is equal to 40. So we will also know from this that C is equal to 4.18, so that's great. We don't know the maths at the minute, do we? But we are told the volume of the solution that we have. And given the fact they've told us that the density is 1 gram per centimetre cubed, that means that every 1 centimetre cubed that you have gives us 1 gram. So if we have 50 centimetre cubed of our limiting factor, our B, then that must mean that we have 50 grams of it. So we can see that the mass is equal to 50 grams. So now we know everything that we need to work out what Q is. So it's 50 times by 4.18 times by 40. And we can use that now to work out that Q is equal to 8,360 joules. So we need to convert that now to kilojoules. So we could say that our Q is equal to 8.360 kilojoules because the conversion simply involves dividing the joules by 1000. So now we have Q in kilojoules. Next up, we need to work out the enthalpy change by taking that Q and dividing it by the number of moles. But we do have a slight problem here. We don't know the number of moles of B, that limiting reactant. So let's work it out. We know the volume, don't we? And we know the concentration. And we know that we can calculate the moles by saying that it's the concentration times the volume over 1000. So by using this then, we could say that moles is equal to 0.10 times by 50 over 1000. So by putting that into our calculator, I make the moles to be equal to 5 times 10 to the minus 3. So now we can work out our enthalpy by saying that it is 8.360 over 5 times 10 to the minus 3. So tapping that away into the calculator is going to give me a value for this delta H of 1,672 kilojoules per mole. And the final check, our step 4, is it actually exothermic or endothermic? So here we can see that the temperature increased from 25 up to 65, and that means that the temperature increased and it means that our enthalpy change is going to be negative. So finally, we add a negative sign in front of our 1672, and now we know our enthalpy change. So that there is our answer to the first question on this page. Okay, so the next question tells us that the standard enthalpy change of combustion can be used to determine the enthalpy changes of formation. So they've given us a table here with some of these enthalpy changes of combustion. And we're simply asked to define the term of standard enthalpy change of combustion and include any standard conditions that are used. So this is a great definition to add to your flashcards if you don't already know it. The definition for this is that the enthalpy change of combustion is the enthalpy change for the complete combustion of 1 mole of a substance under standard conditions. And it's very important in that definition that you have complete combustion in your answer and 1 mole of a substance in your answer. And of course, the standard conditions are implied by the fact that we're defining a standard enthalpy change of combustion. Now, those standard conditions are 298 Kelvin and 1 atmosphere pressure. Now, you might instead have learned the temperature as 25 degrees C and the pressure as 100 kilopascals or 101 kilopascals. Absolutely fine. They all mean the exact same thing and they will all get you the answer in a question like this. Here we're asked to calculate the standard enthalpy change of formation of propane using the equation given below. Now, this question here is a Hess cycle question, but I find a lot of students have a really common problem here in that because they've asked for the standard enthalpy change of formation, they're going to do a formation Hess cycle. But no, that is not what we want to do here. All that matters, I'm going to say it's irrelevant what they ask in the question, all that matters is what data they've given you. And here you can see they have given you the standard enthalpy changes of combustion. So that means that we have to do the Hess cycle for combustion. So let's draw this out then. So we have 3C plus 4H2 makes C3H8, and via complete combustion we'll end up making carbon dioxide and water. Now we need to determine which way round our arrows down to these products are going to go, and we need to remember that this is combustion, so we can completely combust the carbon and the hydrogen into carbon dioxide and water, and we can completely combust the propane into carbon dioxide and water. So both of our arrows here are moving downwards. So now that we have this set up, I would start labeling my arrows with the data that's been given to us. So first off, we're asked to find this enthalpy change of formation. That is the thing that we're asked to calculate. We know what the enthalpy change of combustion is of carbon, and we can see here that we have 3 carbons. So I'm going to write here 3 times minus 394. So next up, we have the hydrogen. We can see we've got 4 hydrogens, and we know that hydrogen has the enthalpy change of combustion of minus 286. So here we've got 4 times minus 286 that we put here. So now, if we look over at the propane, you can see that there's just one of them, and the standard enthalpy change of combustion is minus 2,220. Now at this stage, I would probably tidy up some of my bits. So here, I would add both of these products together to get a single number for these values. So working this out, I get minus 2,326. Okay, so now we've done most of the hard work here, but this brings us to another point where people make a lot of mistakes. So whenever I have a Hess cycle, I like to think, well, what is my start and what is my end point? And obviously we could go directly which is what we're looking for. It's that delta HF. But remembering what the definition of Hess's law is, that enthalpy change is the same regardless of the route that we take. So if we were to take this long way around, we would get the same enthalpy change. So what we want to pay attention to here is, are the arrows going in the same direction? And if they are, you just write down that enthalpy change as it is. So we've got minus 2,326. And then we then have a look at the next part and see here that the arrow, that green arrow, which is where we want to be taking our route, is going in the opposite direction to that enthalpy change of combustion. And that means that we're going to reverse the sign. So it would have been minus 2,220, but now we're going to add 2,220. And if we put this into a calculator now, we will end up getting minus 106 kilojoules per mole. And that value there is our enthalpy change of formation of propane. So we've got our answer. So here we're told that carbon disulfide is a volatile, flammable liquid which is readily combusted to give carbon dioxide and sulfur dioxide. And here we're asked to write the balanced equation for the complete combustion of carbon disulfide. So this is quite different to a lot of the combustions we've done in the past, whereby it's just hydrogen, oxygen and carbon. Here instead we have sulfur as well. And that's why they've given us that little hint in the question about how when we combust it, we make carbon dioxide and sulfur dioxide. So here we've got this CS2, which is the formula of carbon disulfide, so di meaning two. And we're completely combusting it, so we have lots of oxygen, and we're making carbon dioxide and sulfur dioxide. So here, looking at this now, we can see we need to balance it. So initially I can see that the carbons are the same, but the sulfurs are different. We need to multiply the sulfur dioxide by 2 in order to balance the sulfurs. So now that we have done that, the carbons are balanced, the sulfurs are balanced, but now we need to balance the oxygens. So if we look at the product side here, I can see I've got 2 oxygens from the carbon dioxide, and then I have 2 times 2 oxygens from the sulfur dioxide, which makes 2 plus 4, which makes 6. So I've got 6 oxygens on my product side, which means I need 6 oxygens on the reactant side. So that means that I'm going to need 3 O2s to give us those 6 oxygens. So now we're asked to calculate the standard enthalpy change of formation of carbon disulfide using the information given below. So below here you can see we're given a few different enthalpy changes. We're told that the enthalpy change of combustion of carbon disulfide is minus 1,110. We are told that the standard enthalpy change of formation of carbon dioxide is minus 395, and the standard enthalpy change of formation of sulfur dioxide is minus 298. And we're asked to find the standard enthalpy change of formation of carbon disulfide. So I here would probably use the first part of this question as a little bit of a hint as my starting point. So I'm going to write down that balanced equation that we just found up here. And above the arrow, I'm going to write the enthalpy change of combustion of this carbon disulfide. So minus 1,110 kilojoules per mole is the enthalpy change of this combustion reaction that we have here. So if underneath we write all of our elements, because Hess's cycle drawing it is really just like a visual aid to help you do the calculation, we don't have to like literally pick apart and write down all the elements perfectly. I just scribble down elements. So now let's think. The elements form the substances, and so the arrow goes from the elements to the substances. So let's think about what we have been told here. We're told the standard enthalpy change of formation of carbon dioxide is minus 395. So I've written that down here because this arrow represents both the formation of carbon dioxide and the formation of sulfur dioxide. So we also are told that the standard enthalpy change of formation of sulfur dioxide is minus 298, and we have 2 sulfur dioxides. So we're going to do 2 times minus 298. So there we go. Then on the other side, you can see that we have carbon disulfide and oxygen that we make. Well, I say make. Oxygen we don't make. That is just already in its element form. So therefore we have no standard enthalpy change of formation for the oxygen there. So that doesn't have a value associated with it. Whereas the carbon disulfide, that is what we're being asked to find, the enthalpy change of formation of that. So I'm going to write delta HF here, and then I'll just write in brackets next to it CS2, so we remember what that is of. So here in this particular Hess cycle, we can think, well, what is our start point? What is our end point? I could say, okay, I want to start here and I want to end here. To do that, I'm going to have to go along here and then along here. And so again, although we're taking a different route, the enthalpy change will be the same because we're still going from the same initial reactants to the final products. So looking at these then, you can see that we are going along in the same direction as the enthalpy change arrow here. So that means that we're simply going to have that minus 395 plus 2 times minus 298, which gives us minus 991. So we're going to write down that delta HF equals minus 991. And then in the next leg of our journey, you can see that actually we want to go in the opposite direction to the enthalpy change we have there. Our arrows are opposing each other. So that means that we're going to change the sign of that enthalpy change. So instead of it being minus 1110, we're going to add 1110. And that gives us 119 kilojoules per mole. And that there is going to be the standard enthalpy change of formation of carbon sulfide. Finished. So this question here is slightly different because although our equation is given in terms of barium hydroxide and barium carbonate and so on, what they've actually given us here is the enthalpy change of formation of different ions. And we're not used to seeing that, but this is a twist that they could do just to try and throw us off course in the exam. And we just need to hold our heads and think, that's fine, I can still do this. So the way that I would do this is I would probably rewrite out the equation they've given us, but instead any of these aqueous substances, so the barium hydroxide, I'm going to dissociate it. So I can write it as its ions rather than just as the barium hydroxide. If you think about it, it is exactly the same thing. So barium hydroxide will be barium 2 plus 2 OH minus. Everything else here is not aqueous, so we can just carry on with plus CO2 makes barium carbonate plus H2O. So if we think, well, what are the elements, or at least like the components that made this up, then we're going to have our like barium, our oxygen, our hydrogen, our carbon, and so on. I'm just going to write elements though, just to shortcut that part. And I know that I want to do the Hess cycle for formation because they have given me the data for formation. Anything else would be redundant. We just can't do anything with combustion values because we don't have them. So we know that we need to do a Hess cycle for the enthalpy change of formation, which means that the elements are at the bottom and then the arrows will go upwards to show that the elements can form these substances. So looking at this question, you can see that we're looking for the standard enthalpy change for this reaction. So we need to find what delta H is. So let's have a look through the data then and fill in what we can on our Hess cycle. So you can see straight off that we have some barium ions, and we are told the enthalpy change of formation of those. So that is minus 538. Then you can see that we have 2 hydroxide ions, and each of those is minus 230. So we're going to add on 2 times minus 230. And then finally we have some carbon dioxide here. And there's just one of those, so we're just going to add on the minus 394. So at this stage I would probably pop this into a calculator and then see that I have got a value for the total enthalpy changes of formations of the reactants of minus 1,392 kilojoules per mole. So now we're going to move over to the other side and just do the exact same thing over there. You can see we've got 1 barium carbonate, so we have minus 1216, and 1 water, so we're just going to add on this minus 286. So just like we did with the reactants, simplify to get the total enthalpy of formations of the products here, and I make that to be minus 1,502. So now finally we want the enthalpy change of this reaction. So if we think about this, this here would be the start, these reactants, and the products are the end. And we could have gone the direct route, but we also can go the long way around. We can go down here and then up here, and then we still end up at our same destination. So in doing that, you can see that in this section here, our arrows are opposing each other, which means that when we work out what delta H, we want to take this value here, minus 1,392, but change the sign because we're going the opposite direction of that enthalpy change. So we've got positive 1,392, whereas over here on the next leg, we're now going in the same direction. So we're going to keep that sign the same, and it is minus 1,502. So simplifying this, I get an enthalpy change of this reaction to be minus 110 kilojoules per mole, and that there is our answer. So next up, we're told that when carbon dioxide is bubbled through an aqueous solution of barium hydroxide for a longer time, a different reaction occurs. And here we're asked to calculate the standard enthalpy change of formation of the hydrogen carbonate ion. And in this case, we're told that the enthalpy change for this reaction is minus 26 kilojoules per mole. Okay, so here you can see we've still got all of the stuff going on. We're just going to do another Hess cycle using the values given above. So here we have barium carbonate plus carbon dioxide plus water makes Ba2 plus 2 of these hydrogen carbonate ions. So we're told in the question that the enthalpy change of this reaction is minus 26, so we can fill that in now. Again, we're just going to use a Hess cycle with the elements on the bottom, and so the arrows will be moving upwards. Here in this case, we will again fill in all of that information that we had. So we know that the enthalpy change of formation of barium carbonate is minus 1,216. The enthalpy change of formation of carbon dioxide is minus 394. And the enthalpy change of formation of water is minus 236. Adding these up gives us a total enthalpy change of formation for the reactants to be minus 1,896. Over on the other side, we can see that we have the barium ions, and we have one of those. So we've got minus 538. And then we've got 2 hydrogen carbonates, which we don't know. So I'm just going to call each of those enthalpy changes of formations of hydrogen carbonate ions to be X. So we've got 2X here. So now that we have this, we can now write a little formula. So I'm just going to make some space for that here. And let's have a go at calculating this. So again, I like to use the method of like, where are we starting, where are we ending? You can see here that the start of our 2x is over at the elements, and then we're going to end up here. So we could go the direct route, which has an enthalpy change equal to 2x minus 538. Or we could go the long way around, which, remember, is the exact same enthalpy change. That is what Hess's law states to us. So we could go up here and then along here. And you can see there then that in both cases, our arrows that we've just drawn to get from the start to the end are actually in the same direction of our enthalpy changes. So we keep the signs the same. First leg of our journey is minus 1,896 minus 26. So if we simplify that there, we end up getting that 2x minus 538 is equal to minus 1,922. Now all we've got to do here is just a little bit of algebra. If we now add on to that 538, we get that 2x is equal to minus 1,384. And then finally dividing that by 2, I end up finding that my enthalpy change of formation of hydrogen carbonate is equal to minus 692 kilojoules per mole. And that there is our final answer. A chemist determined the enthalpy change of combustion of the compound C4H10O. So we're told that in an experiment, 11.1 grams of that compound was used to heat 25 grams of water. The temperature of the water changes from 32.7 degrees C to 62 degrees C. And we're asked here to calculate the energy released in kilojoules in this experiment. So in this question here, we need to use the equation that Q equals mc delta T. Or you may have learnt it as mc delta theta, but it is the same equation. So here the m relates to the mass of the substance getting heated up. So we could get confused here because they've given us two different masses. But it doesn't matter what the mass is of the compound, it matters what is the mass of the water whose temperature is increasing. So we know that the mass is 25, C is a constant, which is equal to 4.18. In an exam, they will either give this in your data book or in the body of the question. And delta T is the change in temperature. So the change in temperature in this case is going to be 62 minus 32.7. which gives us 29.3. And an important thing to remember here is that delta T, it doesn't matter what the unit is for once. It doesn't matter if it's degrees C or if it's Kelvin, the difference between the temperatures will both be the same. So delta T is equal to 29.3. So now if we multiply all of these three things together, we will get the energy in joules. And then, because the question wants the energy in kilojoules, we will then have to divide that by 1,000 to find it in kilojoules. So initially here, I get 3,061.85 joules, but then dividing it through by 1,000 to convert it to kilojoules, I get 3.06 kilojoules if I round it just to three significant figures. Okay, so next up we're asked to find the enthalpy change of combustion of C4H10O. So here it's important to remember that to find enthalpy change using this experimental method, we take the energy in kilojoules and then divide it by the number of moles of whatever substance it is that has caused this increase or decrease in temperature. So that could be like a fuel or something like that. So for this instance, it will be the number of moles of the C4H10O. So we don't currently know that moles yet. So that's going to be the next little calculation that we're going to need to do to calculate this. So to find moles, we need to do mass over MR. And before we can do that, we need to find out what the MR is of this C4H10O. So we've got 4 times 12 for the carbons, plus 10 times 1 for the hydrogens, and then just plus 16. And that gives us 74. So when working out the number of moles, we're just going to take the mass, which is 11.1, and then divide it by 74. And I make that to be 0.15 moles. So going back to this equation here to find the enthalpy, we will see that delta H equals 3.06 divided by 0.15. And that gives us an enthalpy change equal to 20.4 kilojoules per mole. And the final thing to check here is this an endothermic or an exothermic reaction? Now in this case, you can see that the temperature increases. And because the temperature increases, we can then say that the enthalpy change is negative. So here then, that means that our final answer is minus 20.4 kilojoules per mole. So now we're asked to write down the balanced equation for the combustion of 1 mole of C4H10O. So here, let's do the complete combustion. So C4H10O plus oxygen, and under complete combustion conditions are going to give us carbon dioxide and water. Now let's have a go at balancing this. You can see that we have 4 carbons, which means we're going to have 4 carbon dioxides. I can see that I have 10 hydrogens, which means I'm going to need 5 waters. And finally, let's have a look at all of the oxygens. So over on the product side, I'm going to have 8 oxygens from the carbon dioxide, and I'm going to have 5 oxygens over from the water. So that tallies up to give me 13 oxygens on the product side. Over on the other side, I can see I've got 1 oxygen from my C4H10O, which leaves me with 12 oxygens that need to come from the O2. So because it's O2 and I need 12 oxygens, I'm going to need 6 O2s. And that there is our final answer. So next up, we're told that the theoretical value for the standard enthalpy of combustion of C4H10O is 332.42 kilojoules per mole. And we're asked to explain why the experimental value obtained by the chemist is lower than the theoretical value. So, and you can see it really is quite a lot lower, isn't it? Because we got a value of minus 20.41, and here we're saying, oh, it should have actually been 332. So let's think of some ideas why. And these are going to be good answers to put on a flashcard even, because these come up really, really often. So here we go. So the first point is that there could be heat loss to the surroundings or even heat absorbed by the apparatus. Essentially, not all of that heat from the combustion may be going to directly heating up that water. So that's our point 1. Our point 2 is that there may be incomplete combustion. And if there is incomplete combustion, then that means that there's less efficient combustion and not as much energy is being released from it as potentially could be. So those are 2 great answers that are really, really common for this type of question, so do make sure that you know them. Here we're told that the standard enthalpy change of formation of hexane can be determined indirectly by using the standard enthalpy change of combustion. So first off, we're asked, well, what is the meaning of the term standard enthalpy change of formation? Now, this is a really important definition that you know. It will come up often, and also, as well as just needing to know it, it will really help your understanding when we're doing the Hess cycles, okay? So the standard enthalpy change of formation is defined as the enthalpy change when 1 mole of a compound is formed from its constituent elements in their standard states under standard conditions. Now that there has a few really key bits in it that you need to know. We want to make sure that we know that we refer to 1 mole of a compound, because enthalpy change is always referred to per mole. And we also need to remember we refer to the standard states, because here we have specifically been asked to define the standard enthalpy change formation. So there you are. So there is our definition of standard enthalpy change formation. It is the enthalpy change when 1 mole of a compound is formed from its constituent elements in their standard states under standard conditions. Now we're told that hexane is an organic compound which is used to extract edible oils from seeds and vegetables. We're asked to complete the equation below for the chemical change that can take place to produce the standard enthalpy change of formation of hexane by adding the state symbols. And they've given us a handy little hint here because we don't necessarily know the boiling point of hexane. We're not overly familiar with it as a substance, but we want to show its standard state. And that means the state that it is at room temperature and pressure, which is where that boiling point is important. Because at room temperature, which is 25 degrees, you can see it wouldn't yet have reached its boiling point, which is going to mean that hexane is a liquid at room temperature. Then over to the other bits, carbon is a solid at room temperature, and hydrogen is a gas at room temperature. So here then we have 6 carbons solid plus 7 H2Os, which are gas, makes hexane, which is a liquid. And now we're asked to calculate the standard enthalpy change of formation of hexane using the information given below. So to do this, we need to think, are we going to do a Hess cycle of formation or of combustion? And remember, it doesn't matter what they're asking you for. Not important. What matters is what data they have given you. And honestly, just knowing this trick will stop you making mistakes. I know Hess cycle is a topic that a lot of people really just repeatedly struggle with, repeatedly make mistakes with. But this is why, because they'll ask for the standard enthalpy change formation, and then you will start to do the Hess cycle for formation, but no, you should have done it for combustion. So that's my little top tip for this topic, really, okay? Just always check what data you have been given and use that to help you. Okay, so I'm going to write the equation out again here. And then because they've given me combustion values, I'm going to write my products of combustion underneath. And because it's combustion, I know that I need arrows that are going from the substance down to those products of combustion. And now I'm going to get to work with filling in the numbers from the table that has been given. So I know that I have got 6 carbons. So I need 6 times minus 394. I know that I have 7 hydrogens. So I need to add on 7 times minus 286. And then over on the other side, we just have one of the hexanes. So that's just minus 4,163. So before we go any further, I'm just going to simplify the enthalpy of combustions of the reactants, okay? So I'm just putting that into the calculator to find that total for the reactants gives me minus 4,366. So now we're doing good, we're getting there. So now I would think, okay, I'm getting there now. I need to find the enthalpy change of formation of hexane. And that is this reaction here. Okay, so if we think in terms of the start and the end, I need to start over here and then I'm going to end up here. I could go the direct route, but I could also go the other route because that is what Hess's cycle tells us. Hess's law tells us that regardless of the route that you take, the enthalpy change will be the same. So I'm going to start at the start point and I'm going to travel my way to the end. So looking at that, I can see that we are going in the same direction as the enthalpy change for the reactants. So I'm just going to pop down the number there of minus 4,366, no differences. And then looking at the enthalpy changes of the products there, I can see that my arrow is going in the opposite direction to the enthalpy change arrow. So I'm going to reverse the sign, and instead of minus 4,163, I'm going to use positive 4,163. So that finally gives me there that delta H is equal to minus 203 kilojoules per mole. And so that there is our answer. That is the enthalpy change of formation of hexane. So next up, we're asked to suggest why it is very difficult to determine the standard enthalpy change of formation of hexane directly. So this is only a 1-mark question, so we only need to give one suggestion, and there's a few that you could get. So let's run through some of them. So first off, there's the option that actually many different hydrocarbons would form here, not just the hexane. So it's very hard to pin down that enthalpy change of formation of hexane. So another option is that potentially the activation energy is just too high, so this reaction just won't really take place. And also maybe the reaction is just too slow. So again, because the reaction is too slow, that means that you're going to be there all day trying to observe it, and you're not going to get like measurable results that you can then use to experimentally determine this result. So those are 3 good suggestions as to why it's difficult to determine the standard enthalpy change of formation of hexane directly. Liquefied petroleum gas is a mixture of liquefied propane and butane under high pressure. Here we're asked to calculate the standard enthalpy changes of combustion of propane and butane gas at room temperature. We're given here a collection of all of these different standard enthalpy changes of formation for water, carbon dioxide, propane, and also butane. So to do this, we need to start with balanced equations, and we're going to do these separately. We're going to first start with propane, and then we'll do it for butane. So when propane is completely combusted, we're going to add oxygen, and then we form carbon dioxide and water. We need to balance this equation out. So we need 4 H2Os to make the 4 hydrogens, and we need 3 carbon dioxides to balance with the 3 oxygens. Overall in total there now, we have 6 plus 4, so 10 oxygens. So we're going to need 5 oxygens here. Now, because we have been given the data for standard enthalpy of formation, that means we need the elements at the bottom of our Hess cycle. And our arrows are going to go up because the elements form the substances above. So now looking at what we have, you can see that we know the enthalpy of formation of propane is minus 104. Oxygen is already at its standard state, it's already O2 gas. And over on the other side, we've got 3 CO2s, which are 3 times minus 394, and 4 waters, which is 4 times minus 286. So there we've got everything written down. Let's now just try and tidy up some of these bits. Let's calculate what 3 times minus 394 plus 4 times 286 is. I make that to be minus 2,326. So now we want to get to the bit where we calculate this enthalpy change of combustion of propane. So we're being asked to find this combustion. We need to start here and end over here, but using Hess's law, this enthalpy change is exactly the same regardless of the route that we take. So let's have a go at going this other route here. So you can see that we're going in the opposite direction over on the reactant. So we're going to change the sign. And instead of it being minus 104, it is now just 104. And then over on the other side, we're going in the same direction. So we just keep the sign the same. So it is minus 2,326. So let's simplify this now. Let's put it into a calculator and get a value. So I make this to be minus 2,222 kilojoules per mole. So now for butane, we're going to do exactly the same. We're going to write that balanced equation out. And then we're going to do our Hess cycle. We've already seen it in practice here, so we've got a good idea of what method we need to use. So when balancing this combustion equation, I can see I need 5 waters to get the 10 hydrogens, and I'm going to need 4 carbon dioxides to get the 4 carbons that are in the butane. So to balance the oxygens now, I've got 8 oxygens on the carbon dioxide, 5 from the water. That gives me 13. So I'm going to need 6.5 O2s. So again, we're still given the standard enthalpy change of formation. So I'm going to scribble down the elements here. Arrows need to go up when doing enthalpy change of formation Hess cycles. So we know that the enthalpy change of formation of butane is minus 126. We've now got 4 of the carbon dioxides, and we have got 5 of the waters. So let's simplify those products there. So the enthalpy change of formation of the products. So that simplifies to give me minus 3006. So same as before, we need to find the enthalpy change of combustion. So looking at this, we're starting over here and ending over here. So we can go this route because Hess's law states that the enthalpy change is the same regardless of the route taken. I can see here that my enthalpy change of combustion for butane is going to be equal to 126 minus 3006. And that gives me minus 2,880 kilojoules per mole. So there we are. We have our enthalpy change of combustion of both propane and butane. So now we're asked to calculate the amount of heat needed to increase the temperature of 400 grams of water from 25 degrees C to 85 degrees C. So here, because you can see we're given specific heat capacity, we're given a change in temperature, we know that we need to use the equation Q equals mc delta T. And that Q is our energy, that amount of heat energy needed. So in this case, we're given the mass of the substance getting heated up, that 400 grams of water. We're told that the specific heat capacity is 4.2. And we're given 2 different temperatures from which we can calculate that change in temperature. So 85 minus 25 equals 60 degrees C. So we know that the change in temperature is 60. So if we type those into the calculator, we will get a value for Q. So I make that to be 100,800 joules. Now this question hasn't specified for your answer to be in joules or kilojoules, so long as the unit is correct, it's fine. In chemistry though, it's more likely that you're going to give an energy in kilojoules, so let's also write it in kilojoules. And we do that just by dividing through by 1000, and here then we would get 100.8 kilojoules. And that there will be your answer. So now for the next part of this question, we're asked to calculate the mass of carbon dioxide emitted in each case when the above process, so that release of heat, takes place. So first we need to do this looking at propane as the fuel. So here I think it's important that we sort of write down that balanced equation again that we had for propane's combustion and also get its enthalpy change. So we know that propane plus 5 oxygen makes 3 carbon dioxide and 4 H2Os. We also know that the enthalpy change of that reaction, of the combustion, was equal to minus 2,222 kilojoules per mole. So we said here, didn't we, that the energy released was equal to 100.8 kilojoules. So if we use the fact that the enthalpy change is equal to Q over the number of moles, then we can work out how many moles of propane are required to do this. And then once we know the moles of propane, we can work out the moles of carbon dioxide by using our balanced equation. So here we've got moles equals Q over delta H. Moles is going to then be equal to 100.8 divided by 2,222. Now we don't need to include the negative sign there, because what that negative sign does is it tells us if that energy has been given out or taken in. It doesn't impact the number of moles. Obviously, we can't have a negative number of moles. So putting this into the calculator, I find that the number of moles of propane is 0.0454. So you can see there that that is the moles of propane. Now to find the number of moles of carbon dioxide, we use the fact that we have a 1:3 ratio. So we can work out the moles of carbon dioxide by doing 3 times by 0.0454. And that gives me 0.1362 moles of carbon dioxide. So now we can answer our question and we can work out the mass of carbon dioxide. Now remember that mass we calculate by doing the moles times by the MR. So let's quickly work out the MR of carbon dioxide. It's going to be 12 plus 2 times 16. That gives us 44. So our mass is going to be 0.1362 times by 44. And that gives me a mass there of 5.99 if we round it just to 2 decimal places. Okay, so now we need to do exactly the same thing, but for butane as the fuel. And so because we've already been through our working here, it's going to be that little bit easier. So let's start by writing out our balanced equation for butane. So that is C4H10 plus 6.5 oxygen equals 6 CO2 and 5 waters. So straight up here, let's remind ourselves of what the enthalpy change of combustion was for the combustion of butane, and that was minus 2,880 kilojoules per mole. So let's put this into practice then. Okay, so we know that delta H equals Q over N. We know that N therefore is Q over delta H. We've already used this. Q, though, we know is that 100.8, and now we're dividing it by a different enthalpy. Remember that the sign doesn't affect this calculation because we can't have negative moles anyway, so we'll just use the magnitude of that delta H. So this gives us moles equals 0.035, and that there is the number of moles that we have of the butane, so 0.035. And so using our molar ratios, you can see for this reaction we have a 1:4 ratio. Here we have 0.14 moles of carbon dioxide. So that means that we can work out the mass of carbon dioxide by doing moles times by the MR. The moles in this case is 0.14. The MR is still the same, it's still carbon dioxide. So putting this into the calculator, we get 6.16 grams. So there we have calculated our two different masses of carbon dioxide dependent on whether we're combusting propane or butane. Okay, so now we're asked to identify which fuel will be more environmentally friendly and explain why so, based on the calculation from 7.3. So the answer here is going to be propane. And the reason why it is more environmentally friendly is because, as you can see above, less carbon dioxide is released compared to butane to release the same amount of heat. So if we want to get the same amount of heat from burning some fuel, you will end up releasing much more carbon dioxide when burning butane instead of propane. So that means propane is more environmentally friendly. So here we've got quite a big wordy question. We're told that a student wants to determine the enthalpy change of this following reaction at room temperature. So here we've got sodium hydrogen carbonate decomposing to form sodium carbonate and water and carbon dioxide. So we're told that he followed the following steps to determine the enthalpy change for this reaction. You can see in step 1, we took 0.08 moles of sodium hydrogen carbonate and we added them to 100 centimetre cubed of 1 mole per decimetre cubed HCl solution. And we saw the temperature decrease by 5 degrees C. In step 2, 0.04 moles of sodium carbonate added to 100 centimetre cubed of 1 mole per decimetre cubed HCl again. But this time, the solution increased in temperature by 3.5 degrees. So to start us off here, they just ask us to write the balanced chemical equation that's happening in each step. So in the first step, we had our sodium hydrogen carbonate and it's being added to hydrochloric acid. So hydrogen carbonates react in a very similar way to just carbonates. We end up getting a salt, water and carbon dioxide. So let's write that down and then see what might need balancing. So the salt we make here is sodium chloride. We make our CO2 and our water, having a little look of any balancing that may be needed. And I can see that here it does appear to be balanced. So now with step 2, we know that we had sodium carbonate added to HCl solution. So again here, it is going to be a very, very similar equation, probably just the balancing will be slightly different. So here we've got HCl, we're going to still make sodium chloride and carbon dioxide and H2O. Here though, we're going to need to do some balancing. So looking at this here, I think it is already balanced. So there we are. So now we're asked to calculate the standard enthalpy change for the reaction between sodium hydrogen carbonate and dilute HCl. So our step 1 here. So if we go and have a look at the information that we were given, you can see that we know the volume of the solution, and we're told to assume here that the density is just 1 gram per centimetre cubed. That tells us that when we have a volume of 100 centimetre cubed, we've actually got a mass equal to 100 grams. C, they tell us to use the value of just 4.0. And the temperature change, we know, is equal to 5. So we can use this information to work out the heat energy. So here we know that Q equals mc delta T. So Q will then equal 100 times by 4.0 times by 5. And that ends up giving us a value for the energy equal to 2000 joules. So that isn't what has been asked from us though. Okay, if you look at the question, they want the enthalpy change. So to find the enthalpy change, we need to get the energy in kilojoules. So we're going to divide through by 1000 and therefore get Q to be equal to 2 kilojoules. And then delta H, that enthalpy change, is equal to Q divided by the number of moles. And in this case, in this question, they've actually been quite nice to us and they have told us the number of moles. They told us it's 0.08. So here we have 2 divided by 0.08. And that gives us an enthalpy change equal to 25. Finally, let's make sure we include our units and also check the sign of the enthalpy change. Here we know that the temperature decreased, so it's an endothermic reaction. So that means that delta H is positive 25 kilojoules per mole. So now we're asked to calculate the standard enthalpy change for the reaction between sodium carbonate and dilute HCl. So this is from step 2. So thinking of what we know from the previous question, again, the mass in this step 2, it has a mass of 100 grams, because just like in the previous question, we're looking at a volume of the solution of 100 centimetre cubed. And due to the density, 1 centimetre cubed is equal to 1 gram. So here, 100 centimetres cubed is 100 grams. We're told to use C equals 4.0, and we're told that the change in temperature is equal to 3.5 degrees C. So using these values, we can get that Q equals mc delta T, which is 100 times by 4 times by 3.5. And that gives us 1,400 joules, which we can convert to kilojoules simply by dividing by 1,000. So we know that Q is equal to 1.4 kilojoules. So now to get the actual enthalpy change, we need to do Q divided by N. So that is 1.4 divided by 0.04 in this case. And that gives us 35 kilojoules per mole. And the final check to always do with these questions is this an endothermic or an exothermic reaction? So here, because we're told that the temperature increases, that means that we have an exothermic reaction, which means that we're going to have a little negative sign for our enthalpy change. So the enthalpy change is actually minus 35 kilojoules per mole. Okay, so next up, we're asked to calculate the standard enthalpy change for the decomposition of 2 moles of sodium hydrogen carbonate by completing the Hess cycle below. So first things first, let's just balance this reaction. Here I can see that I'm going to need 2 of the sodium hydrogen carbonate to make the sodium carbonate, CO2 and water. So that's all looking balanced now. So this is a really different type of Hess cycle. It's not one using formation, it's not one using combustion, but it's one that is going to use the previous 2 reactions that we wrote down, those 2 balanced equations, and we're going to piece them together in this Hess cycle to then be able to construct this enthalpy change that's required here. So first things first, let's just remind ourselves of what those equations were earlier. So we looked at the reaction of sodium hydrogen carbonate with HCl, and we saw that it made sodium chloride, carbon dioxide and water, and that there's balanced. And we also saw that sodium carbonate plus HCl makes NaCl, CO2 and water also. But in this case, we need to give it a quick balance. So what we can see here is we can see that we can use these equations in this Hess cycle. So let me colour code this a bit. Imagine if we had sodium hydrogen carbonate and HCl, and they react together just like in this reaction. Well, we know what's going to get made then, don't we? We know we will make sodium chloride, carbon dioxide and water. So here, that is going to be what we write down below here. We're going to get sodium chloride, we're going to get carbon dioxide, and we're going to get H2O. Now, one extra thing to add is, of course, here, just due to the balancing of the top reaction, we've got 2 of each of those. So because this equation that we had here is just a 1 to 1 to 1, etc. ratio, we just need to double everything. So we have 2 NaCl, we have 2 CO2, and we have 2 waters. So let's insert our state symbols. So we've got aqueous for the sodium chloride, carbon dioxide is a gas, and water is a liquid. So far so good here. So next up, you can see that we have this sodium carbonate plus CO2 plus water over on this side here. Now, let us here just ignore for a moment the carbon dioxide and the water. And let us imagine that we're going to react it with 2 HCl, just like we did previously. Well, in that case, when we react 1 sodium carbonate with 2 HCl, we end up making 2 NaCl and just 1 carbon dioxide and 1 H2O. So we would have made just 1 of each of these, but there's 2. But that's why we've got a carbon dioxide up here and a water up here. They don't take part in the reaction, but they increase the tally of 1 CO2 and 1 water to then make 2, as we have in this little balanced reaction. Okay, so now that we know this, now that we've got our Hess cycle all set up, we can have a go at doing our calculation. So earlier on, we said that the enthalpy change for the reaction with sodium hydrogen carbonate was equal to 25 kilojoules per mole. Now, here you can see that this region represents that equation. But there's not 1 mole of sodium hydrogen carbonate, there are 2 moles of sodium hydrogen carbonate. So that means that we're going to have 2 times 25 kilojoules of energy there. So let's have a look on the other side then. So we said that the reaction of sodium carbonate with HCl had an enthalpy change of minus 35. So let's write down minus 35 there on that side. We're being asked to find the enthalpy change of this top part of this reaction. So if we remember the start and the end of it, we know that we could just go this way and then up here. So using that, we can see that as we go along here, we have an enthalpy change of 50. As we go up here, it's in the opposite direction of that blue arrow for the enthalpy change. So we're going to reverse the sign of our minus 35 and instead add 35. And that is going to give us 85 kilojoules per mole. And that is our enthalpy change of the reaction. So here we're told that enthalpy change of formation can't be calculated directly, therefore an indirect method using enthalpy change of combustion can be used. So here we're asked to explain the meaning of the term standard enthalpy change of combustion and to include the standard conditions that are used. So this here is a definition question. Here we need to define the enthalpy change of combustion. And so we need to know that it is the enthalpy change that occurs when 1 mole of a substance completely combusts, or we could say reacts fully in oxygen, under standard conditions. Now there in that definition, there's a few really important things to say. We need to identify it's 1 mole. We need to say that we have complete combustion, or say words to that effect. And we need to mention those standard conditions. Now in this particular question, we need to include those standard conditions. So the standard pressure is 100 kilopascals, or we could say 1 atmosphere, or 101 kilopascals. And the standard temperature is 298 Kelvin, or you could also write 25 degrees C. Just make sure that you include your units. That's great. So that is our definition. If you don't have that memorised, then I would suggest that you start repeating it, quizzing yourself on it and getting it stuck in your head. So now we're told that we have 3 enthalpy changes of combustion. And remember, it's always the data that's given that matters. It's not the actual thing they're asking in the question, it's that data. So here we're asked to construct a labelled energy cycle to show how these values could be used to calculate the enthalpy change of formation of C3H8O. So, like we said, all that matters is the data that's given. So because it's enthalpy changes of combustion, we want to construct a Hess cycle that has carbon dioxide and water on the bottom. So because it's an enthalpy change of combustion, we need our arrows to point downwards so that we can see that we're combusting those bits on the top to form carbon dioxide and water. So looking through everything here, we can see that the enthalpy change of combustion of carbon is minus 394 per mole. So we have 3 times minus 394 done. We've got the hydrogen, which is minus 286. So we're going to add on 4 because we've got 4 moles times by minus 286. The oxygen doesn't combust. It is one of the things needed for combustion, in fact, so there's no enthalpy change of combustion for oxygen. And then over on the other side, we just have our C3H8O. So there's just one of them. So we're just going to add in minus 4125. So over on the reactant side, I would simplify this using a calculator. So doing that gives me a total enthalpy change of combustion for the reactant to be minus 2,326. So now at this point, we have a nice labelled energy cycle that can be used to calculate the enthalpy change of formation of C3H8O. And that's what we're going to do over on the next part of the question. So I'm just going to redraw my little Hess cycle here just so that we can refer back to it in a nice simplified form, just to save us a little bit of time. So we knew that we have minus 4125 here, and over here we have minus 2326. So to work out the standard enthalpy change of formation of C3H8O, we need to think, well, we need to start here and we need to end here. So we could go in the direct route, but that's not going to help us here because we don't know that. But we can use Hess's law. So we can move down this way and then up to here, then we still go from the same start point and end at the same end point. So in doing that, we've moved in the same direction as that first enthalpy change. So we can say that the enthalpy change of formation is equal to minus 2,326. But then over here, you see, we're going in the opposite direction to that enthalpy change. Now that means that we want to reverse the sign of this enthalpy change of minus 4,125. So we're going to make it positive. So now, finding that enthalpy change of formation, we need to just put this into a calculator, and I make that to be 1,799 kilojoules per mole. And that there is our answer. So really great work for getting to the end of this set of exam questions. I really hope that I was able to help you with these questions and hope they're making a lot more sense now. Now, have a little break now, and then a bit later, go away, have a go at some more questions and see if you can still do them. Great work, guys. Bye.
Ouch! This is why in some videos I explain scratches.